அனு அனு
Sir?
காயத்ரி.
Yes, sir.
இது ரெக்கார்டிங் வந்து நான் ஆஃப் பண்ணி வச்சிருக்கிறேன். நீ
Okay,
6
sir.
மணிக்கு இவரு வந்ததுக்கு அப்புறமா அதை ரெக்கார்டிங் ஆன் பண்ணிக்கோ.
Okay, sir. Okay, sir.
சரியாமா?
சரி சார் பண்ணிடுறேன் சார்.
ஓகே. மறந்துடாத
ஓகே சார்.
மறந்துடாத.
ஓகே சார். ஓகே சார்.
ரெக்கார்டிங் ஆட் பண்ணணும். பிளஸ் வந்து இவங்க எல்லாத்தையும் கோஹோஸ்டா மாத்தணும், ராமானுஜம் சாரையும்.
ஓகே சார்.
ஓகேம்மா.
ஓகே.
A very warm welcome to day 2 of our faculty development program on deep learning and computer vision in the field of clinical research. After an insightful day 1, where we explored the fundamentals of AI driven clinical image analysis, we are excited to delve deeper into more advanced topics today. Today's sessions will bring together renowned experts in AI, deep learning, and medical imaging to share their knowledge and research, helping us bridge the gap between theory and real world applications. We will explore topics ranging from deep learning techniques in medical diagnostics to the role of AI in clinical decision making. With an engaging lineup of sessions, Day 2 promises to be an enriching experience, equipping us with practical insights and the latest advancements in AI powered healthcare solutions. Let's begin the day with our first session.
We will now start today's session on deep feed-forward networks by Dr. Ramanujam Sir, Assistant Professor at NIT Silchar. With over 12 years of experience in AI, deep learning, and human activity recognition, he has contributed significantly to smart home automation, IoT-based healthcare, and real-time predictive systems. Holding a PhD from Anna University, he is a senior member of IEEE and a life member of ISTE. His research focuses on AI-driven solutions for multiple resident activity recognition, anomaly detection, and clinical data analysis with extensive publications in top-tier journals and conferences. This session will cover deep feed-forward networks with their architecture and applications, followed by convolutional neural networks and their role in medical imaging and AI-assisted diagnostics. His work in computer vision and AI-driven healthcare is shaping the future of precision medicine and automated clinical decision-making. We now invite Dr. Ramanujam Sir to lead the session on deep feed-forward networks and CNN in medical applications. Over to you, sir.
Thank you, Gayatri. Hope my voice is audible.
Yes, sir, your voice is audible.
First of all, I would like to thank Tyagarajar College of Engineering and AICT Atal for giving me this opportunity. Actually, I have grown up in Tyagarajar College of Engineering. The place I have reached today is because of Tyagarajar College of Engineering. I thank Dr. S. Parthasarathi sir, Dr. Chandra Kumar, and Dr. Sasideka for giving me this opportunity to share my knowledge on this deep learning and convolutional neural network models. Let me share my screen. Hope my screen is visible to you all.
Yes, sir, it is visible.
Thank you. So the first topic that I'm going to cover is about the deep feed-forward neural network. In this session, I'll be discussing more about the neural network, the backpropagation, how to train the neural network model, what are all the optimization techniques available to train this neural network model, and all these things. A kind request to all the participants, please be interactive in this session. You can ask some doubts or you can ask some queries so that it will be helpful for me to proceed further, right? So the first topic is about the deep feed-forward neural network. The presentation is for the AICT Atal FDP on deep learning and computer vision in the field of clinical research. So before entering into this session, so I want to know the person I have shown in this PPT. May I know who is this? May I know who is this?
Actually, the participants are answering in the chat box to the hosts.
Okay.
They are responding as Sachin Tendulkar.
Acha, okay. So everyone are sharing that it is Sachin Tendulkar, right? Okay. Then this.
Yes, sir, they are responding as Obama.
Okay. Actually, the name is Barack Obama.
Yes.
Anyone knows the name of this person?
They're saying it's Henry.
Henry. Only Henry?
Yes. Henry Olango.
Ah, good. Actually, the people, those who have watched early 90s or 200s, 2000, then we know that the person, third person is Henry Olango. It's a famous Zimbabwe bowler. Why I have shown this images in the sense we all know about this Sachin Tendulkar very well. We all know very well about this Barack Obama. But the thing is Henry Olango. What we are coming to say here is how we know the environment, how we learn from the environment, how we gained knowledge from the environment. This is how we used to behave in the real time life or real time world. That is what we say it as a human brain. So we know that. How do we know their names? Based on some incidents or based on watching their cricket matches or their political interviews, we know that this person is Sachin Tendulkar, this person is Barack Obama, or this person is Henry Wallango. How we remember this? We used to remember in our human brain. Human brain is nothing but it's a complex model. It is completely non-linear and it performs something like a parallel computer, right? It controls your thoughts, memory, emotion, touch, etc., etc., etc. We used to say that the human brain is the main nervous or the central nervous system that controls your entire human body, how to react for the environment, right? How it works? It works based on the structural constituents. We say it as a neurons. In the brain and the spinal cord, we have at least approximately 86 billion neurons that communicate it through some electrical signals and neurotransmitters. Okay, this is what we say it is a human brain. Why we are saying about this human brain? What is the relation between this human brain with this artificial neural network model? The neural network model is a kind of a machine that is designed in a way as like a human brain to perform some function of interest. Very importantly, the artificial intelligence and the real intelligence is completely different. The artificial intelligence, we can do certain process. We cannot do all the process as like a human being. But in the natural intelligence, you can do anything if your brain gives you the approval. So in the neural network is nothing but it's a machine designed to model the way the brain performs. So what we can say it as, it's a parallel distributed processor comprises of some processing units. Processing units is nothing but the neurons, or we say it as a nodes, which have the natural prosperity of storing some experiential knowledge and making it available for use. What kind of use it is? It is for all kind of real world applications. That is what we say it as a neural network model. So let me give an example about this human brain and the artificial neural network. Whenever you see a food, what we used to think, we used to eat. Whenever you see a fruit, we used to eat. When you see a snake, we used to run away from that place. When an elephant is running ferociously, what we used to do? We used to run from that place. We used to safeguard ourselves. So what I'm coming to say here is, the stimulus is the environment, okay, or what you are seeing or what you are visualizing or what you are hearing. The senses is what we say it is a stimulus. What we sense from the real world environment, that is called as a senses. From this, we are giving it to the receptor. Receptor is nothing but we touch or we analyze or visualize or we view through some human body objects. That is what we say it is a receptors, which is given to our central nervous system, which is nothing but the brain. It analyzes the effects and it will be given to the response. What kind of response if we do? This is the complete central nervous system. Stimulus is the environment. Receptor is the nothing but the sensory organ which we use to sense from that stimulus. The human brain will instruct you what to do next based on the sense that it has attained. The effectors will be giving back the response. Let me show an example. This is the person who tries to touch the candle with the flame. So this flame is nothing but the stimulus. This flame is nothing but the stimulus. Based on the stimulus, if it touches with the finger, this finger is your receptor. This receptor will be sending you the information to the human brain right? Which will do some process and it will be returning back to the sensory organ, nothing but the effector, to take back the finger immediately from the fire, right? This is how the neural network is going to perform in the real time. So what is the stimulus and what is the receptor? What is the central nervous system? How the effectors will be, how the response will be, that is what we are going to discuss it now. So what about this ANN? ANN is nothing but it simulates the network of neurons. It simulates the network of neurons. As like a human brain, we have the multiple neurons here that will able to learn things as like a human, right? For example, it may be in the weather prediction, it may be in the object recognition, it may be in the self-driving car, it may be in the rainfall forecasting, it may be the gold forecasting, or any kind of real world applications. We are going to use this ANN. This is the difference between the typical neuron with the artificial neuron. So let me explain about this typical neuron. In this typical neuron, we have the dendrites. Dendrites is nothing but the input coming from the other neuron. Axon is the output, or nothing but the which is connected with the next neuron, that is called as an axon. The cell body or the soma, which is the main process, or we say it as a nucleus. This is going to do all the kind of process. When you connect it from here, this is a single neuron for the artificial thing. So this complete process is the neuron. These things are the dendrites. These are the dendrites, and these are, we say it as a weights. We say it as a synapse. We say it as a synapse. And this is a complete neuron. This will do all the process and which will give you the output. What kind of response it has to give it to the output, real world environment. That is called as the response. So what we are coming to say, what is the need of this input? What is the need of this weight? That we'll be discussing it now one by one. So the cell nucleus or the soma, nothing but the node. It processes the signals and it contains a nucleus. Whatever the data that you are giving to the neuron, that will be processed by this soma or nothing but the node. Dendrites is nothing but the input, which is given by the real world examples, or it can be the input from the other neuron. Synapse are nothing but the weights. It used to control the strength of the connections between the neurons. For example, in your lifetime, you may have some very crucial incidents, or you may have some critical incidents that you will never forget it. Why? What is the reason? Because the brain stores that information very specifically by giving you more importance. That is why you are not forgetting that incident in your lifetime. If you are don't remembering any kind of incidents, that incidents may not have that much of importance or significance. So that kind of storage is completely possible because of this weights. So when you go to the mathematical formulation, if you want to give more importance to a particular weight, particular input, the weight of that particular input has to be very high. Then only the neural network model can do the complete process. Axon is nothing but the output given to the next neuron or nothing but the muscles. So this is a single neuron. Okay. The single neuron has the input units. This is the input units. This input unit is nothing but the nodes, input nodes we have. This will never do any kind of process. This will simply take the input from the real world and it will give it to the neuron. So the neuron contains two modules. First one is a summing unit. What is a summing unit? The summing unit is nothing but it used to sum up all the weights. It used to sum up all the weights with the input, whatever we are getting into it. Then we have the activation function. The activation function introduces the non-linearity. I'll be explaining all these things in the next slide. So before that, I'll be giving you an overview. The activation function is nothing but it introduces the non-linearity. What is in by non-linearity? Why we have to go for this non-linearity? Actually, the data, whatever we give, That may be in terms of any number, but this nonlinearity will convert that number to the value of either 0 to 1, or it will convert the value from -1 to 1, or it converts the value from -1 by 2 to +1 by 2. That is the purpose of nonlinearity. Okay. So very first model, network model, is the McCulloch-Pitts neuron model. What is the purpose of this McCulloch-Pitts neuron model? This McCulloch-Pitts neuron model is the first model designed as like a traditional or the typical neuron. It works only for the decision making of either 0 or 1. It deals only with the binary data. Then in 1958, Franklin Rosenblatt has introduced the model called as a perceptron model. What is the purpose of this model? This model has the weight adjustments to solve some linearly separable problems. I will say what is a linearly separable problem. Okay, later on I'll be explaining to you. Then in 1986, we understood that, okay, using the perceptron model, it is not possible for us to solve linearly inseparable data. So that is why we need to go for multiple layers of perceptron. We say it as a multi-layer perceptron model. Along with the multi-layer perceptron, they introduced a concept called as back propagation. What is in by back propagation? Let me say you a small example. We used to drive a bicycle from the early childhood days. We have never used to drive the bicycle at the very first instant. How we used to drive? First we used to take start. Then we used to go for a small distance. Then we used to fall down. Again we used to wake up. Again we used to drive. Again we used to fall down. Again we used to start. Again we used to run. Again we used to fall down. What is the purpose of this falling down? We exactly don't know how to balance a bicycle. So we used to fall down. Whenever you fall down, you will have an idea that, okay, this is the issue that we are getting fallen down. So we used to correct that particular mistake so that next time we used to rectify our mistake so that we used to drive it properly. What is simply a back propagation coming from this example? How we rectify the error. When we rectify the error, our performance will be good. Nothing but we used to drive the bicycle in a good way. That is the purpose of multi-layer perceptron. So with this concept, we'll be entering into the artificial neural network. Okay. So what is an artificial neural network? It has multiple layers. It has a multiple layers of mathematical processing to make sense of the information what you are feeding into it. You see here, we have 3 layers. This is layer number 1. This is layer number 2. And this is layer number 3. This totally we have 3 layers. All the 3 layers we have the nodes, or we say it as a neurons. Okay. This layer is what we say it as a input layer. This layer is what we say it as a hidden layer. For every neural network model, you must have only one input layer and only one output layer, but you may have n number of hidden layers. Why? I will explain. Dozens to millions of units arranged in a series of layers. That means each and every unit will have n number of neurons. For example, let us take an input layer. How to fix the number of neurons in the input layer? Okay. So I'm going to give an image, or we say it as a column vector. This is the column vector we have. The size of the column vector is 1 cross 128. This is the input we are going to give it to the neural network model. Okay. Similar way, you have multiple column vectors, that is n cross 128. What is this 128 is? This 128 is nothing but the futures. 128 is nothing but the futures or the characteristics of particular object. Okay. So what you are going to do in the sense, you are going to pass this 128 number of futures into this input layer. So what you will get x1, x2 up to x128. Okay. Now I have a question. Now I have a two-dimensional image. This image size is something like 16 cross 16. In this case, how the input will be given to the input layer? Can you have any guess? Any guess for the 16 cross 16? Any idea here? How many inputs you have to pass for the input layer? How many number of units you have to pass for the input layer? If the image size is 16 cross 16. If it is a one-dimensional thing, I have 1 cross 128. So I am giving the number of input unit as 128 number of units. If it is a two-dimensional image, my image size is 16 cross 16. Then what will be my number of units in my input layer? Anugayatri, any message in the chat box?
256.
256. How it is 256? We have to convert this 16 cross 16 into a one-dimensional column vector, which will become as 1 cross 256. Sorry. So which will be given as an input to the neural network model. Okay. Then we have, that is, as I said, the input layer receives the input from the outside world that used to process it, or whatever that you wants to learn from it. That is the input layer that used to get it. But input layer will never do any kind of process. Input layer will just get the data from the outside world. That is the only thing. Coming to the hidden layer. Hidden layer, what is the purpose of the hidden layer? Used to extract the information, or used to do the processing. What kind of processing? It does the non-linearity. What is a non-linearity? Whatever the data that you pass, that is converted to the value of the output. For example, you may give n number of value here. Maybe something like some numbers is given here, something like minus 0.1, 0.2, 0.3, something like this. When I feed all this into this particular hidden layer, this hidden layer have some non-linearity. Let us take this non-linearity as nothing but the activation function. This activation function is something like, let us say, sigmoid activation function. This sigmoid activation function will convert minus infinity to plus infinity with the value of 0 to 1. So whatever the input you are giving with the range of minus infinity to plus infinity, that will be squashed into the value of 0 to 1. That is the purpose of nonlinearity here, right? So what you are getting from here, in the sense, the data is converted in a nonlinear way that transforms the input to a particular output. So each and every layer is completely connected. That is why we say it as a fully connected neural network model. Each and every layer has to be connected with the consecutive layers. For example, this is an input layer. I have n number of nodes in my input layer. All these n number of nodes are connected with the n number of units in the hidden layer. You see that x1 is connected with the h1 through this w11. X2 is connected with this H1 using the weight W21. Xn is connected to this H1 using the weight W31. Why it is weighted? What is the need for making this as a weight? For an example, let us take a H1. H1 is taking 3 inputs. Let us take X1, X2, and X3. It is a sum of inputs with its weight. So let it be something like W11, X2 into W21, and X3 into W31. Of these three, I want to give more importance to the input X1. So let me assign this weight as 1. I don't want to give that much of importance to x2. Let us take this as 0.5. I don't want to give the importance to input x3 at all. So we can make it as 0. So what happens? X1 becomes x1 plus 0.5 times of x2. Got it? So this is the purpose of the weight. Whether you want to store the information in the neural network or not, whether you want to take that data for learning or not, that is decided by the weight. So higher the value of weights, greater the influence of the unit, similar to the human brain. As like in your real-time life, you may remember lot number of informations in your human brain. That is because of the incidents, or that is because of the environment, or that is because of the time. The same thing, if you want to remember some data, some input given by the model, whether you want to store it or not, that is decided by the weights. So in here, the data goes through each and every unit. For example, when you pass from the input layer, from the input layer, it will pass through the hidden layer. From the hidden layer, it passes through the output layer. At the output layer, you will be getting an output, right? It is not that it will be dropped out in the hidden layer, it will be dropped out of the output layer. Whatever the input you are giving, that input will be taken to all the number of consecutive layers and finally given to the final output, right? This is the complete artificial neural network model. So output layer, where the network responds to the data, whatever it is given as an input, and the processed input, that is very, very important. Whatever the data that you are given, that is completely a processed input. So first, let us discuss about the individual neuron. See here, which one is neuron? This is a neuron. This is also a neuron, and this is also a neuron. You can say this is a neurons, but we say it as an input neurons. Input neurons means it will simply take an input and it will give it as an input to the next layer. It will never do any kind of mathematical process. That is the input neurons. However, the neurons in the hidden layer and the neurons in the output layer will do this kind of process. Okay. So first let us discuss about the individual neuron. Individual neuron is nothing but, this neuron is nothing but the perceptron. We also say it as a perceptron, which was introduced by Franklin Rosenblatt. Okay, we also say it as a Rosenblatt perceptron model, or we simply say it as a perceptron model. Okay, this is a perceptron model that I have. So first and foremost thing, set of input. What is the set of inputs? This x1, x2, x3 is a set of inputs that we have, right? Then we have the synapses. Synapses is nothing but the weights, which is given with the each and every individual input, that is called as a synapses, or nothing but the connection link. Then we have something called as a bias. What is a bias? Whether you want to increase the net input or you want to decrease the net input, that is the purpose of the bias. Okay, if you want to increase the net input, you can increase it. If you want to decrease the net input, you can decrease it. That is the purpose of a bias. So you see that this bias is given as an additional thing. Okay, if required, you can use it. If you don't want, you can remove it. How we can decide this? By placing the value of 0 or 1. 0 means there won't be any bias. 1 means 100% you'll be using a bias. If you want to give some other value, you can give any other value. Then we have the process called as summing unit. What is mean by a summing unit? Whatever the inputs it is coming to the neuron, all the units along with its weight is multiplied and summed up. That is why we say this as a summing unit. I repeat, whatever the inputs it is entering into the neuron, all the neurons are multiplied with its weight and all the input are summed up with its weight. That is the purpose of this summing unit. We say this as a linear combiner. We have multiple names. One is a linear combiner. We have another also called as a summing unit. We get this Vk. What is this Vk? Mathematically, summation of I is equal to 1 to 3 because we have 3 nodes, 1, 2 and 3. Xi is multiplied with its weight and then additionally it is added with the bias. So that is why they say that as increase or decrease the net input. This Vk is what we say it as the local induced field. We used to say it as a local induced field. right? Then we have the important process called as an activation function. What is the purpose of an activation function? It introduces a nonlinearity, then it squash the data, whatever the range it has, even minus infinity also be there, plus infinity also be there, or it can be any range from minus infinity to plus infinity. This will be converted to a certain value, certain range. That is the purpose of an activation function. We have n number of activation functions, something like threshold activation function. It is also known as stepwise activation function, or we say it as a Heaviside activation function. We also say it as a signum activation function. We have something like a sigmoid. Sigmoid is the most probably used activation function in the logistic regression, and it is used with a neural network model. This sigmoid activation function will squash the value with the range of 0 to 1. We have something like a hyperbolic tangent, which will convert the value from -1 to +1. We have the pairwise linear approximation, which converts the values from -1/2 to +1/2. So we are giving the input in this input unit, which is taken care by the weights. Weight is nothing but the impact of the input given to the neuron. Then in the neuron, we have two modules. First module is a summing unit, which used to sum up all the input along with its weight, then which is given as an input to the activation function. This activation function will convert the input which is given to the range of 0 to 1 or -1 to 1 or -1/2 to +1/2. There is activation function called as ReLU. You know very well about this ReLU. The ReLU is nothing but which is mostly used with convolutional neural network model. Why it is mostly used with the convolutional neural network model? Why not it is used with the neural network model? Actually, here we are using the final output as either 0 or 1. Sorry, 1 minute. We are using this output as either 0 or 1. If you get ReLU is nothing but which will give you something like max of 0, x. If you get a negative value, we'll be printing the value as 0. Else we'll be printing the value as the x. Whatever the positive value we'll get, that will be given as the output. So in neural network model, we will be never discussing about this ReLU. We'll be using only about the sigmoid or the hyperbolic tangent functions. Right. So let us implement a simple OR gate. We all know about the OR gate. OR gate is nothing but it's a kind of AND operation or OR operation. It's a kind of a simple OR operations. That is a plus. 0 with 0 is 0. 0 with 1 is 1. 1 with 0 is 1. 1 with 1 is 1. So what we want to do, in the sense, we want to design the neural network first. So what is the input we have? We have x1, we have x2. We are going to implement the OR gate only for a binary signal. So x1 and x2. So I decided to fix the input unit as x1 and x2. If you perform for 3 inputs, x1, x2, x3, you add one more node. If you want to perform for 4 inputs, you make it as x1, x2, x3, x4. Very importantly, we are doing this OR gate only for the single neuron. We are not doing it for multi-layer perceptron. So we have x1, we have x2. We know very well that what is the y value? This is called as an actual y value. Right? This is called as an actual y value, or we say it as a ground truth of our OR gate. Actual or our ground truth. So 0 with 0 is 0, 0 with 1 is 1, 1 with 0 is 1, 1 with 1 is 1. So now we know that we have two inputs, x1 and x2, which is connected to the summing unit. We know to decide that what are all the weights we have to give it. So we have to fix the weights and we have to fix the bias. Now you may ask a question that how you fix the weights as W1 and W2 as 1. Why not it can be 0? Or why not it can be 0.1? Why not it can be 0.5? Yes, it is up to us. You can use any kind of an weight. It can be 0 or it can be 0.1 or it can be 0.2 or 0.5. For simple demonstration, I decided to fix this weight as 1. You may ask a question that why you have fixed this bias value as 0? Why not it can be -1? Yes, it is up to you. You can fix the bias value, right? Next, we decided these weights. Next one is we have fixed this summing unit, right? Next one is we have to fix the activation function. You can use any activation function since it is a simple, what we say it is an OR gate. We have gone for the threshold activation function. What is the mean by this threshold activation function? Okay, first let me explain about this local induced field. That is this Vk. How you will be calculating this Vk? We know that Vk is nothing but product of this W1 into X1 and product of this W2 into X1, X2. Then we will be summing up this with this bias. So X1 W1 plus X2 W2 plus this bias, right? So what is this threshold? Threshold is nothing but whenever the Vk value is getting greater than or equals to 1, we'll be getting the final output. That is the Y cap. Y cap is equal to the value of 1 whenever the Vk value is greater than or equals to 1, 0 otherwise. You may ask whether it is the fixed 1 or you can change anything. Yes, you can change anything, no problem. But most of the time, we used to have only this Vk value, that is the local induced value greater than or equals to 1. Will not go above that and will not go less than that also, right? So let us explain. We know that this is Vk, this is our Vk, and this is the activation function we have decided, right? And then we are going for this x1, x2, and y with what is a Vk. So we know that x1 is 0, x2 is 0, actual output is y, right? When you substitute this value with these equations, okay, so 0 into anything will be 0, 0 into anything will be 0, plus bias is also 0. So we'll be getting this value of Vk as 0. So as per this equation, threshold activation function, whenever the Vk value is greater than or equals to 1, then only we'll be getting the value of 1, otherwise 0. So we are getting the value as 0. So actual Y we required is 0 and the machine that decides use also 0. So both Y and Y cap is equals. Now let us go to the second instance. Second instance is nothing but x1 is 0, x2 is 1. Actual output we required is 1. Let us come to this Vk. What is this Vk? It is x1 into W1 plus x2 into W2 plus B. So when you do the process, we are getting this Vk value as 1, right? Now what will be the output of this Y cap? Y cap is nothing but if the Vk value is greater than or equal to 1, we'll be getting the value as 1. So we are getting the value as 1. So whether Y is equals to Y cap, yes, Y is equal to 1 and Y cap is also equal to 1. So both are the same, right? Now the same thing, when you go for the third instance is 1, 0. What is our Y value? Actual value is 1. The expected, that is what we calculated, is also 1. Why? Because when you do this process with this equation, x1 into W1 is 1, then x2 into W2 will be 0, bias will be 0. So we'll be getting this Vk as 1. So we'll be getting this Y and Y cap as 1. So both are same. Now when you go to the last instance is nothing but both are same, right? So to what we say it as both x1 and x2 are 1. So what is the output we required here? Y is also 1. So when we calculate this Vk is also 1. So when you go for this Y cap, both is 1. So when you take this, both are same. So this is the simplest single neuron model. For this simplest single neuron model, we have identified some weights W1, W2 with some bias, and we did the calculations for all the 4 instances. For all the 4 instances, we got the exact output. Whatever we required, that is the output, we already got it. So here no need of fine tuning anything. We don't want to do any kind of other process. This OR gate is called as a linearly separable data. What is meant by linearly separable data? When you have some data points, right? Let me give an example here. So we have this as 0, 0, This is 1, 0. This is 0, 1. This is 1, 1. So what is 0, 0? 0, 0 actual value we required is 0. 1, 0 we required the value as 1. 0, 1 is also we require the value of 1. 1, 1 we require the value of 1. So these 3 points require the value of 1. Only this point requires the value of 0. So what we can do in the sense, we can simply draw a straight line here so that these 3 points will be getting the value of 1. This point will be getting the value of 0. This is called as a linearly separable problem. This kind of single neuron will easily process the linearly separable data. It is difficult to process a linearly inseparable data. What is linearly inseparable data? Linearly inseparable data, matlab, it is an XOR gate. Let us go for an XOR gate so that you can understand it. So let us go for the XOR gate. XOR gate has a small change. If both the inputs are the same, we'll be getting as 0. If both the inputs are different, we'll be getting the value of 1, right? So in this case, same single neuron is considered, okay? Same weights are considered and the same bias is considered. There is no change at all. Same activation function. The local induced field is also the same. The threshold activation function is taken here. So as per the equation, we know that whenever the Vk value is greater or equal to 1, we'll be getting that output as 1, right? So you see here why it is linearly inseparable data. This is 0, 0. This is 1, 0. This is 0, 1. And this is 1, 1. So what is 0, 0? It is equals to the value of 0. This is equal to the value of 0. And 0, 1, this is equal to the value of 1. 1, 0, this is equal to the value of 1. 1, 1, this is equal to the value of 0. But here, I cannot draw a single line. You see here, if I draw a single line here, this point is 1, this point is 0, this point is 1. There is a misclassification accuracy. Yes. So if I draw a line here, again, you see here, this is 0, 1, this is 1, 0. If I draw a line here, this point is 0, this point is 1, this point is 1, this point is 0, and this point is 0. So if I draw a line here, these 2 points are 0, 1, and these 2 points are 1, 0. So we cannot solve this problem. That is what we said as a linearly inseparable problem. So how to avoid this? Okay, first let me show the calculations. Then I will say what to do next. So the same process I did for it. So same equations we have. So actual y, both are same. We required this value of 1. Output is also 1. And we required this 1. Output is also 1. But when you go for both 1, we require the value of 0. But we are getting the output as 1. So both are not the same. So you'll be getting the output as no. So the misclassification accuracy is something like 1 by 4, which is 0.25, right? So your model can perform better for 75% of accuracy. 25% of accuracy is not correct. So in this case, how to solve this kind of a linearly inseparable problem? So for that, we are going for the process. Let me show this again, the same diagram. Whatever I have drawn earlier, the same diagram I have given to you, right? So to avoid this kind of linearly inseparable cases, we are going for the process called as feed-forward neural network or the multi-layer perceptor. Any doubt up to now? Anyone? If you have any doubt, you can ask me or you can message me. So I give a recap of this. I discussed something about the human brain. I discussed something about the artificial neural network. And then I discussed something about the modules of different layers of artificial neural network. What are all the different layers and how each and every layers will be and I discussed about the single neuron system, how a single neuron will work, and what are all the modules available with a single neuron. Using the single neuron, we have implemented a OR gate and we have implemented an XOR gate, right? Up to this, we discussed about the single neuron. Any doubts you have, you can ask me. Any doubts?
So as of now, they've asked VK is 2 when both X1 and X2 are 1.
1 minute. Yeah, that might be technically what we used to say is when VK is greater or equal to 1, obviously we'll be getting this output as 1, right? Yes, I agree that when you do the multiplication, we'll be getting this VK value as 2. But as per the equation, whenever it is greater or equal to 1, we'll be getting the output as 1. So that's why I written as 1. Technically or mathematically, it is 2.
So, and they're asking if how can we collaborate CNN concept with chemical engineering, civil engineering, electrical.
That we will speak it at the last session. Okay. Any other doubts with this?
Yes, sir. They're asking if you could tell how sigmoid relo activation functions are different and why sigmoid activation function is used mostly.
Okay. I'll be going to the next session based on that only. Based on that, we will discuss, right? Okay.
Yes.
Let me proceed with this. So we are going to discuss about this feed forward neural network. Okay. Feed forward. That means we are going to give the input to the model that will be taken in a forward direction. Forward direction in the sense we'll be going from this phase to this phase. That is input layer to the output layer. That is what we say it as a feed forward neural network. There won't be any cycles. There won't be any cycles here. That is the purpose of feed forward neural network model. Information flows in one direction. That is from the input to the output. That is why we say this as a feed forward neural network model. It consists of, again, as I said, it consists of only one input layer, one or more hidden layers, and an output layer. Okay. So if you want to perform any kind of classifications, it is dependent on you, how many number of hidden layers you want to fix. So input layer consists of neurons that receive the input data. That nothing but the input data is nothing but that represents the futures of the input. If you have the input of n cross 256, then you will be having 256 number of nodes in the input unit. If it is n cross 128, then we'll be using 128 number of units in the input unit. That is the purpose of the input unit. So hidden layers, one or more hidden layers are placed. That is the purpose of learning the complex patterns in the data. That is the purpose of learning the complex patterns in the data. Each neuron in the hidden layers apply the weighted sum of the inputs with the nonlinear activation function. As I said earlier, whatever we have the input, that is multiplied with the weights, and which is given as a sum as an input to the hidden neuron. That hidden neuron has a nonlinear activation function that converts that into the value of 0 or 1. Finally, the output layer that provides a final output, right? Here, it depends upon the number of neurons. The number of neurons depends upon the problem what you are going to use. If it is a regression problem, you can use a single neuron here. If it is a binary classification, you can go for single neuron. If it is a multi-class classification, you have to use the number of neurons that depends upon the number of classes. Okay. So number of outputs is depends upon the regression problem or the classification problem. Binary means you can use only one neuron with activation function as sigmoid activation function. So greater than 0.5 will have one class, less than 0.5 will have another class. If it is multi-class classification, you can go for the softmax. Based on the probabilistic score, we'll be getting the final output of the particular class. So very importantly, each connection between the neuron is having the weights that weights are adjusted during the training process to minimize the error in predictions, especially the learning rule. Okay, that is what we say it is the learning rule. So learning rule is nothing but it used to reduces the training, it uses to reduces the error during the training process. That is the purpose of the learning rule. As I said earlier, if I want to drive a bicycle, first time I used to fall down, second time also I used to fall down, third time also I used to fall down. Why I am falling down this many number of times? That is because of my error. I am doing some mistakes. So each time when I recover from that error by learning something, how to balance my bicycle, then I can drive my bicycle better. That is why we used to divide the data. The data can be divided into something like training data and something like test data. Most of the data is given to the training. Maybe something like 70% of data is given to training and 30% of data is given to testing. Right? Why? What is the need? If I give 70% of the data, so that the remaining 30% of the data can be tested very accurately. If you give only 10% of data for training and 90% of data for testing, this is not good. Yes. As like our regular examinations, we used to take 30 hours of class or 40 hours of class and we used to conduct the examinations for 2 hours. The same thing, we used to train more. If our model trains better, then our performance will be better. That is the purpose of this training. This learning rules, that is what we are going to derive it now. So this is the simple feed-forward neural network model. So I have the 3 neurons, X1, X2, X3, and I have a dead neuron, X1 and H2. All the units in the input layer is connected with all the units in the hidden layer. You see here, one is connected with this one. So that is why I mentioned this as W11. 2 is connected with this one. So that is why I mentioned this as W21. 3 is connected with this one. So that is why I mentioned this as 3, 1. So the weight notation is based on the input to the connected node. So input node is 1, the connected node is 1. So we made it as W11. Input node is 2 and connected node is 1. So we make it as 2, 1. So this input units will take the data and it will give it to the hidden units. So what does the hidden units consist of, or what it will process? See, the node processes the data that comes in. Pi, the same thing I have written here, pi of this equations. This equation is nothing but the Vk, that is the local induced field. Okay, so pi of Vk will be the final output, which is given from this hidden nodes, maybe here or here, whatever it may be, right? For each and every unit, we'll be having Vk. Vk is nothing but the sum of weights along with its input with the bias, and which is given to the activation function. That activation function can be any kind of an activation function. Based on that, we'll be taking an output. So here the hidden units, here we'll be taking the outputs, and then again, which is given as an input to the output layer, or nothing but the output unit, which will be giving you only one value in terms of 0 to 1. Okay, so let me give an example. So what about this output? How the output is coming, right? Let us take the activation function as pi, right? This pi will be taking this data, this entire data here. So which is nothing but 1 by 1 plus e to the power of minus x, which is nothing but the sigmoid activation function. So I am writing this as an OI, right? OI is nothing but the output for individual unit. So it will be giving you the value of 1 by 1 plus e to the power of minus x. 1 by 1 plus e to the power of minus x, which is the normal equation. Actually, we used to say it as 1 by 1 plus e to the power of minus alpha x. Alpha x is nothing but, when you draw this equation, this is 0. So this will be plus infinity and this will be minus infinity. When alpha is equal to 1, we'll be getting this equation like this. And when alpha 2 is equal to 2, we'll be getting this equation like this. When alpha is equal to 3, it goes on like this. When it goes on like this, it goes on like this, right? Based on the alpha, the equation, the S curve will change. Sigmoid means nothing but the S curve. it will be perfect S curve. It changes according to the alpha value, right? But we used to fix as the value of alpha is equal to 1. Let me take a small example. How you are going to predict the output using the feed-forward neural network model. We have only the two instances. Two instances means this is instance number 1, this is instance number 2. X1, X2, X3, and what is the output we required? Y. What is this? This is the output predicted by our neural network model, right? So let us take this as 0.3, 0.2, 0.3. Now, how many number of weights we required to connect this model? So we have 3 units in the input layer and 2 units in the hidden layer, and we have 1 unit in the output layer, right? Can you please say how many number of weights it required to make it as fully connected? Any idea here? How many?
They are saying it's 3, sir.
Only 3. Okay.
8,
8,
6,
6,
again a 6, sir.
6. Okay. You see, I have missed out this bias here. Actually, bias is applicable only for your hidden units and then output units. So you will have one more bias here. We'll have one more bias here, and we'll have one more bias here, right? So how to calculate the number of units in the input into the number of units in the hidden layer? Let us see. Number of units in the input layer into number of units in the hidden layer. So we have 3 units in the input layer, which is 3. 2 layers in the input unit, so 2. So this level, only this level we have 6. And when you take these two, number of neurons in the hidden layer into number of units in the output layer. So we have 2 in the hidden and only 1 in the output. So 2 into 1 will be 2. Finally, the number of bias nodes. So bias, you can use it only with the hidden layer and the output layer. You cannot use it with the, what we say, it is an input layer, because you are not going to increase the value of any kind of an input layer. So which will be totally 11. So 3 plus 3 2 is 6, 6 plus 2 is 8, 8 plus 3 is 11, right? Because I missed out the bias in this diagram. Next, what we have to do, we have to fix these weights. How to fix these weights, right? So we can randomly assign a value. It can be very close to 0. Okay, or there are some other methods like Xavier method or cohort method. There are n number of methods available, but we are not supposed to use that kind of models. We are going to use the value very close to 0, right? If you initialize the value of 0, you will not be getting the proper output. It leads to underfitting. So that is why we are going for the process of initializing very close to the value of 0. So you see here, so I have initialized my weights and the bias W11, W21, W31, W12, W22, W32, so and so, and I have decided for all the values, right? Now I slightly change my equation for the better understanding. You see here, this H1 is divided into two half. That is, it is having 2 modules. Similar way, this is also having 2 modules. Let us take this H1, neuron number H1. Neuron number H1 is having IH1. So this is having something like IH1, and similar way this is having IH2. What is this? Nothing but this is an input, or nothing but the VK, which is entering into the process. Okay. So X1 into W11 plus X2 into W21 plus X3 into W31 plus the bias B1, right? Similar way, high H2, X1 into W12 plus X2 into W22 plus X3 into W32 plus bias B2. So this is actually nothing but the VK of the individual neuron. You got my point? This is nothing but the VK of the individual neuron. Then what happens? This high H1 is given to the activation function, so that which will be giving you something like O, right? Let me come to that. You see here, now this is IH1, this is IH2, and we have something like OH1 and this is OH2 because each neuron is having two modules. This module is nothing but the input. This module is the output given by that neuron. This is the input entering into this neuron. This is the output given by this neuron. Similar way, you will be having something like this. What is this? This is something the input and which is giving you the output, and this is the final Y cap, right? So if you do some mathematical calculations, you can understand. Okay. So what about this OH1? OH1 is nothing but 1 by 1 plus e to the power of minus IH1. What is the activation function I have used? I have used sigmoid. Here also I have used sigmoid. Here also I have used sigmoid. So OH1 is sigmoid, OH2 is sigmoid. Similar way, Y cap. What about this Y cap? Y cap I have written as a single expression. You see this is nothing but the input, right? WH1 into OH1. See, WH1 into OH1 plus WH2 plus OH2 plus the bias, right? So which is given with plus bias. Okay. So when you come to this, right, now you see IH1 we have calculated x1 into W11 plus x2 into W21 plus x3 into W31 plus bias, which is giving you the value of 0.11. Let us go for this high H2, which is giving you the value of 0.74. When I put these values into this OH1 and OH2, I'm getting the value of 0.568. As I told you earlier, whatever the input it generates, when you put it with the sigmoid activation function, which will convert you to the value of 0 to 1, right? That is the purpose of a sigmoid activation function. Similar way, OH2 is giving you the value of 0.699. So when I give these two input into my Y cap, what about this Y cap? This is my Y cap. Here only we are going to predict this Y cap. So when I give it to this Y cap, 1 by E plus WH1. WH1 is nothing but the input between the hidden unit and the output unit. WH2 is the input weight between the hidden unit 2 and the output into OH1. OH1 is nothing but which is given from here. OH2 is given from here. So altogether we will be getting the value of 0.5565. What is the predicted output we have? 0.5565. But what we required the value of Y. But we got the value was 0.5565. So what you are getting is it is something less than 0.4. So this is the problem with the neural network model. It may be because of the weights what you have considered, because the weights, it has been assigned by us randomly. There is no fixation by any kind of process. We did it manually or randomly. That is the reason we are getting this as 0.5565. So what you want to do next, in the sense, you have to adjust the weight so that the neural network model may perform better for your next input. Okay. So what you are going to do here is we are going for the back propagation. Okay. We are going for the back propagation. What is meant by back propagation? The back propagation is nothing but that is based on the loss, what we have got it, based on the loss, we used to update the weights. Okay, you see here, back propagation is used to train the neural network by adjusting the weights based on the error. What kind of error? Error is nothing but the actual with the predicted output. That is the difference. That is called as an error. We used to say it as a loss function. Okay, the loss function used to quantify the error, and based on that error, we used to adjust its weights. That is the purpose of this back propagation. This back propagation is done by means of n number of optimization techniques, maybe like stochastic gradient descent or batch gradient descent, mini batch gradient descent. There are n number of descent algorithms available. Based on that, we are going to update it. I am going to speak something about the stochastic gradient descent. Okay. Before that, we want to know what is the loss function, right? So we have n number of loss functions again. If it is a regression based problem, you can use the mean squared error. If it is a classification problem, You can use binary cross entropy or categorical cross entropy, or we can go for the sparse categorical cross entropy, right? What is a binary cross entropy? Binary cross entropy means you have a one hot vector that is 0 or 1, which is represented for the binary class. If in that case, you can go for this binary cross entropy. In case of multi-class, you can go for this categorical cross entropy, right? In case if your classes are represented in terms of numbers, maybe like 1, 2, 3, instead of the one hot vector, then you can go for the sparse categorical cross entropy. If it is a regression problem, you can go for the mean squared error, or you can go for the mean absolute error, or you can even go for the root mean squared error, right? This is a difference between the loss functions that you are going to use it, right? Let me give. So the same neural network model, whatever we have used, the same network model only we are going to use it now, right? In this, for the better understanding, instead of H1, I make it as 4. Instead of H2, I make it as 5. Instead of H6, I made it as, output, I make it as Y. So you are going to take the output with this Y6, okay? So accordingly, I changed my weights because 1 is connected with this 4. So I made it as W14. 2 is connected with this 4. So W24. 3 is connected with this 5. So I make it as W35. 2 is connected with this 5. So W25, so and so. 4 is connected with this 6. So W46. 5 is connected with this 6. So 56, right? So we know that the loss function is only for the output unit. So our output unit is number 6. So L6, and that too, it is for binary class classification. So I have taken a binary cross entropy. Why I used a natural logarithm instead of log? Because whenever you do the differentiation, partial differentiation, both will be the same. Actually, the natural logarithm is used in Python. However, log is used with the normal mathematical calculations. So what is actually the gradient descent? What is the purpose? You see here, this diagram, this is the initial random values we have initialized. So what we are going to do in the sense, we are going to take the descent, nothing but the slope. That is a derivative of the cost function. Based on the derivative of the cost function, we are going to reduce, or we are going to minimize this, the error, right? So this is the error, right? So this error will reduce it. At some point, we are getting this minimum. This is the weights. Okay. Our weights will move in this direction. Our error will get reduced. How we are going to learn, how we are going to take a partial derivative, right? Based on something like what we said as the learning rate. Okay. This learning rate is very, very important. What is the learning rate? How quickly your model get optimized for your weights. That is what we say it is a learning rate. We are not supposed to fix the learning rate very high. Actually, learning rate should be in the value of 0 to 1. 0 means it will never learn. 1 means it will learn very quickly. So what I am suggesting is your value should be something like 0 to 1. Okay. Don't fix 0 and don't fix 1. It should be the value of 0 to 1. Okay. So what you are going to do next, in a sense, we are going to do this gradient descent, or nothing but the back propagation process. So what you are going to do in the sense, we are going to calculate the gradient descent, nothing but the partial derivative of all the weights starting from the loss. That is loss with respect to the weight. That is what we are saying it as a gradient descent. So you see here, gradient descent with respect to the weight W46. That means we have totally 1, 2, 3, 4, totally 11 weights are there along with the bias. So we have to calculate the partial derivative for all the 11 weights, including the bias, so that your model can be updated properly. How to calculate it? So what is the gradient descent? So what is the loss because of this weight? That is what we say it as a gradient descent. Okay. Mathematically, when you say it is a partial derivative of L6 with respect to W46. But when you say theoretically, what will be the impact of weight W46 to the loss function L6? Right? That is what we used to say it as a chain rule. Okay. This chain rule will come in the reverse direction. since it's a feed forward, that input will be taken from the input layer to the output layer, but the back propagation will be taken from the loss function to the input layer. Okay. So let us take this loss function with respect to this W46, how it will take. So as I said earlier, dou L6 by dou W46, nothing but what is the impact of this W46 to this L6? That is what the partial derivative is. So how we are going to calculate based on the chain rule, right? So when I speak in the forward direction, this W46 is intruding into this. We know that this is having I6 and this is having O6. And 4, we have I4 and O4. 5, we have I5 and O5. Right? When you put it here, this W46 will first influence this I6. Because of this I6, there will be some influence with this O6. Because of this O6, there will be some influence on this I6. Right? This is in the forward direction. When you write it in the reverse direction, that is what I have written. Partial derivative of L6 because of this Y6. Y6 is nothing but the O6. Right? Both are same. Then this I6 is influencing this Y6. So that is why I written as Y6 by I6. Then I6 is influencing this W46. That is why I written as I6 by W46. Right? I repeat again. I am going to calculate the gradient descent for each and every weight. Right? How you are going to calculate the gradient descent? Gradient descent is nothing but the partial derivative of loss function with respect to the weights, individual weights. That is what we said as a gradient descent. So let us take the node number 6. We know that node number 6 has two modules. One will be the entry, that is the input. Another one will be the output, O6. Similar way, 5, I5 and O5. Similar way, 4. When you take 4, I4 and O4. Okay. So what happens? First, we are going to calculate the partial derivative of this loss function to the weights 4, 6. So we know very well that this W46 is entering into this input I6. Because of this I6, there is a change with this O6. That is O6 is nothing but the Y6. Because of this, there will be a change with this L6. So this is how the chain rule is working on it. So chain rule, we have to write it in the backwards direction, starting from the output to the weight. So partial derivative of L6 with respect to Y6 cap. So L6 with Y6 cap. Y6 with input I6. Y6 with input I6. Then I6 with respect to W46. This is how the chain rule will work. So first let us solve this L6 by Y6 cap. So this is our L6. When you do the partial derivative with this Y6 cap, right? You see this dou L6 by dou Y6 cap. So when you do the natural logarithm, when you take a derivative of this Y6 cap, this will come down to the denominator. This will come down to the denominator, right? Okay. So I am not entering into the perfect differentiation. So I am directly showing you the results. Now, what you have to do, we have to calculate the derivative of Y6 cap with I6. Please do remember that Y6 cap is nothing but this is the process which is taken and which is the input. Okay, let me redraw this here. So Y6 cap is the output and I6 is the input. The I6 is converted to Y6 cap because of the activation function which is given here. Yes, do you remember? Pi of I6 is nothing but will be giving you the Y6. So when you do the differentiation of Y6 cap with I6, so dou Y6 by dou I6, nothing but dou of 1 by 1 plus e to the power of minus I6. Why I am getting using this activation function here? Because whenever I give the input, that is taken as an output because of my activation function. So I am differentiating my activation function, right? So when I do the differentiation of this, first it is solved like this. ei6 by 1 plus e to the power of minus I6. Then I split that 1 plus e to the power of minus I6 the whole square. So it will become something like 1 by 1 plus e to the power of minus I6 into 1 by 1 plus e to the power of minus I6. Then what happens? This is nothing but again what we say it as this is the pi of I6. Yes. right? Then into, again, this will be 1 by 1 plus e to the power of minus I6, right? So how we can rewrite this? Pi of I6 is nothing but your Y6 cap. Again, this can be rewritten as 1 minus of Y6 cap. Okay, I will show you in the next slide. You see here, so ei6 minus divided by 1 plus e to the power of minus I6 the whole square. So how we can write this? Sigma is nothing but the activation function, pi of I6 into 1 minus of sigma of I6, which is nothing but Y6 cap into 1 minus of Y6 cap, right? This is taken from here. Okay, when you solve this expression, you will be getting this Y6 cap into 1 minus of Y6 cap. Let me explain you here. 1 by 1 plus e to the power of minus I6 into e to the power of minus I6 divided by 1 plus e to the power of minus I6. So what happens? This will be the activation function, nothing but sigma of I6. Again, this becomes, how we can rewrite this? 1 minus of 1 by 1 plus e to the power of minus I6. So nothing but sigma of I6 into 1 minus of sigma of I6, which is nothing but Y6 cap into 1 minus of Y6 cap. This is how this equation comes. Then at last we'll have something like dou I6 by dou W46. Please do remember that this is your I6. Your I6 is getting the input from W46 into this 4 and W56 into this 5. That is what I have written here. So this 4 is nothing but which will be giving you the output of O4 and which will be giving you the output of O5. So dou of O4 into W46 and O5 into W56 divided by W of 56. When you do the differentiation, this and this will be strike out. This part will be completely 0. So you'll be getting the answer as 0, 4. Got it? So altogether, so dou L6 by dou W46, we'll be taking this value. So let us take all together this value, right? So we have taken from the previous slide. Altogether it is given like this. So when you do the simplification of this equation, we'll be getting this dou L6 by dou 46 as minus Y6 cap into O4. So what I'm coming to say here, the loss function because of this weight W46 is getting the value of difference of Y6 minus Y6 cap into O4. That is the difference between the actual with the predicted value of the output given by this 4. That is, this is O4. Let us take this 5. This is O5. Okay. So what will be the impact? So dou of L6 divided by dou of W56 will be same. Negative of Y6 minus Y6 cap, actual minus predicted into this output, that is O5. Got it? The same equation, same kind of equation. So this is because of W46, this is because of W56. Now, what we are going to do in the sense, we are going for the next two process, what we said is a W14, then W24. We have to do the differentiation. So how we are going to do the differentiation for this process? Okay, let us take this W14. So the W14 will influence, this is I4 and this is O4, and this O4 will influence with this W46, nothing but this will be I6 and this will be O6, and this O6 will be giving you this Y6, right? So you see here, dou L6 by dou Y6. So dou L6 by dou Y6, dou Y6 by Y6 or O6, both are the same. So Y6 will be giving you the impact of this I6. I6 is giving you the impact of this O4, and O4 is giving the impact of this I4. I4 is giving the impact of this W14. Maybe like W24 also, whatever it may be. So both are the same. So I repeat, we have this L6. The L6 have an influence because of this Y6 cap. This Y6 cap is because of this I6, right? This I6 is having an impact because of this O4. O4 is having an impact because of this I4. This I4 will have an impact of W14, or I4 will have an impact of W24, right? Like this, the data has to process. So now let us solve this dou L6 by dou W24. Let us take W24. So first, dou L6 by dou Y6 cap and dou Y6 cap by dou I6. So we will be getting it as minus Y6 cap. How we are getting this? You see here. This is the value taken from this. This complete value is taken from this, right? When you this two partial derivative expressions is giving you this value. So when you solve this, when you what do you say this and simplify this expression, we'll be getting this as Y6 minus Y6 cap. Same thing. When you take this 2, I'll be getting this minus Y6 cap, right? Now we have this as I6 and this as O4. Okay. Now when you do the differentiation of I6 with the O4, what you will be getting it? Say I6 is getting an input of W46 multiplied with this O4, and I6 is getting a weight of, you see, W46 into O4 and W56 into O5, right? When you do the differentiation with this O4, this will be 0 and O4 will get cancelled. Then we'll be getting this W46, right? Now this is over. Now we have to go for this O4 by I4. O4 by I4 is nothing but the activation function what we are using. Simply dou O4 by dou I4 will be, sorry. This will be O4 into 1 minus of O4, right? So see that O4 into 1 minus of O4. Finally, we have this dou I4 by dou W24. When you take this I4 with this dou W24, when you do the multiplication, how we will do the how will we do the partial differentiation? I4 is getting an input from W14. You see here. I4 is getting an input from W14 into X1 with this W24 into X2, W34 into X3. Right? When you do this with the W24, this will cancel, and these two will cancel. This 2 will be 0, and this will cancel. You'll be getting only this X2. So you'll be getting an output as X2. So altogether, you see here, dou L6 by dou W24 is minus of Y6 minus Y6 cap into W46, O4 into 1 minus of O4 into X2. So we'll simplify this expression. We'll simplify this expression something like this is the gradient descent output to the hidden layer. Right? So output to the hidden layer in the sense from here to here. Okay. So we have written something like Yj minus Yj cap. This is written as del J into OI. Now gradient descent for the hidden layer to the input layer. Hidden layer to input layer is nothing but something like this complete part is written as something like del of Jk multiplied with this input. Okay. What we are coming to say here in the sense, when you track from, for example, when you update this W34, right? This is the difference between actual with the predicted. Actually, there is a mistake here. Actually, it should be 4. I made a small mistake. Sorry for this. Okay. So when you come from the reverse direction, okay, it will be coming with Yj minus Yj cap. That is actual minus predicted into this weight, into the output, into 1 minus of output into the Xi. The same process will take place, right? I will draw you this diagram. Let us take this. When you come for this W24, or it may be W15, W15 will be dou L6 by dou W15 will be minus of Y6 minus Y6 cap. That is the difference, right? Then after that, we have a weight because we are traveling, we are going to travel in this way. We are going to travel in this way. So W46. Then we have this node. So O4 into 1 minus of O4. Then the input, what we are given from here to here. So let us take this W24. So this will be X will be X2. Similar thing, if you go for dou L6 by dou W15, which will be minus our 15 is here, right? Our 15 is here. So it will come from here, here, then it will come here, then it will reach here. So this is dou 15. So Y6 minus Y6 cap into W56 because we are coming in this direction. So W56, then we have something like O5. This is our O5 into 1 minus of O5. Then we have the input of X1. This is what we have done here. So altogether, it is written like this as a generalized equation. So what we are going to do in the sense, this is only the gradient descent. Next, what we have to do in the sense, we have to update these weights. How to update these weights? Because for each and every instance of the data, you have to update the weights. What is the purpose of updating the weights? If you update the weights, then only you'll come to know that whether the performance of the neural network model is good or not. So weight, what are the weight that you have? Old weight plus lambda. Lambda is nothing but the learning rate. How quickly your model converge or how quickly your model adapts to the data, that is called as a learning rate, right? So you have to fix the lambda from 0 to 1, right? With this del is nothing but the gradient descent. Okay, you may ask a question that these many time the lambda value, that is the whatever the weight we have calculated, which is coming with a negative. But when you do this with the delta of Wij, this minus and this minus will cut off so that your weights will be something in terms of positive. Got it? So this is called as the learning rules. This is called as the learning rules. This learning rule is called as a perceptron learning rule. This perceptron learning rule is a kind of a supervised learning rule. That is, we updated the weights because of the actual and the predicted target class label. There are some other learning rules called as a Hebbian learning rule. That kind of learning rules are unsupervised learning rule. There we used to update the weights without knowing the targeted class label, right? Similar way, you have to update the weights for the bias using the same kind of a gradient descent process. So for every instances of data, you have to update the weight, you have to update the bias. Based on the updated weight and the bias, you'll be taking the next instance. Based on the next instance, we'll be going for the third instance. Based on the difference, we'll be updating the weight. Again, based on the difference, we'll be updating the weight. Like this, you have to continuously update the weights. So if you continuously update the weights at one point of time, your model will perform better. Okay. So this is how the feed forward neural network model will work in the forward direction, and it will work in the backward direction, or we say it as a back propagation process. Okay. This feed forward neural network, we say it as a fully connected neural network. This fully connected neural network model is used in the convolutional neural network layer, that is specifically for future classification. However, the convolutional layers will take the data and it used to extract the data. This fully connected neural network model will take the numerical value or the features from the convolutional layers, and it will does the classification process. Okay, that's all about this feed forward neural network model. Someone was asking about why we are using this sigmoidal activation function. Why can't we use with ReLU? Okay, so whenever you use with the sigmoidal activation function, your weights will not go for 0, right? If your weights are sometimes coming to the negative value, or which is very close to 0, then it will leads to the value of 0. Then the gradient will become vanish, right? Because neural network is something very complex than what we say it as the convolutional neural network model. In the convolutional neural network model, our back propagation process is something different. In the neural network model, our back propagation is something different. If, for example, let us take this partial derivative. If this partial derivative is coming to the value of 0, then all these values becomes 0 because of this partial derivative, right? That is the reason we are going for the sigmoidal activation function, or we'll be using only for the hyperbolic tangent functions. We will not use threshold activation function, or we will never use ReLU activation function. Okay. This is the reason we are going for this sigmoid and the hyperbolic tangent functions, right? Any other doubts you can ask me. If you want to know very clear about this neural network model, you can go for some book called as Pattern Recognition by Bishop. That book, the best book to read about neural network models. Okay, very good book to read about this neural network model.
Sir, sorry to interrupt. Can we take a 10-minute break, sir?
Yeah. Please. Sure.
Okay. So, participants, let us take a 10-minute break. The next session, titled Convolution Neural Network for Clinical Datasets, will begin at 7:40 p.m. Huh? Sir, can you hear me?
Yes, please.
Yes, sir. Sir, can we resume?
Yeah.
Thank
Can I
you.
start with the second session?
Yes, sir.
Yeah, before that, I want to know something from the participants. Actually, I have two content. One is with the convolutional neural network model, the basics, how to fix the number of layers, how to fix the parameters, all these things. Second one is something about the convolutional neural network model with the attention mechanisms. It is up to the participants, whichever you want, I will discuss. Whether you want me to discuss about the basic convolutional neural network model or you want to discuss about the attention mechanisms. Which one you want? Both.
Sir, they're asking CNN basics will be fine.
But I am not getting that message. You are getting that message.
Yes, sir. Actually, they are directly messaging to the host. We have enabled that
Okay.
option.
Acha, okay. So basic CNN model, Manyun has given this basic CNN model. Okay.
Yes, sir.
Actually, we can discuss in both the way. That is, CNN model can be discussed and how the back propagation works. But as one person has asked how to use this convolutional neural network model with the chemical engineering process. See,
Yes.
whatever the data that we have, for all the data, we can use the convolutional neural network model. Let me open these things.
Also, some participants are also asking about both, like conveying the both topics.
Conveying the both topic, I am ready to take it if you extend the session up to 10 or 10:30.
Sir.
So let me share my screen. Yeah, I think my screen is visible, right?
Yes, sir.
Okay. So first and foremost thing, this is about the convolutional neural network with the hyperparameter tuning. I will say it in a layman language. This convolutional neural network model, when you have to use it. Okay. For example, you are going to the vegetable shop or vegetable market. How do you know that this is an apple or this is an brinjal or this is an bottle gourd? How do you know these things? Whenever you are going to the vegetable market, you are knowing that this is a tomato or this is what we say it as uh, brinjal or this is a tomato or this is an apple. How do you know these things? As like Sachin Tendulkar or as like Henry Wallango or as like Barack Obama, we know the values or someone has taught us if the apple means it should be red color, round in shape, it is having the weight of 100 to 150 grams, like that, right? In the other case, when you go for the snake guard, it will be green color, it will be length, right? It requires something like circumference will be somewhat thin, like that. So how to do or how to identify the objects, how you have been taught, that is very, very important. So this convolutional neural network model comes under the deep learning concept. First of all, you must know what is the deep learning, what is the machine learning. Actually, I am giving you that this is an apple. I'm giving you that this is an brinjal. How I am defining that? Apple means red color, round in shape. It has to weight from 100 to 120 grams or 100 to 150 grams. Brinjal, violet color or green color. The weight should be so and so. If this is the way, if I teach you, that is the purpose of machine learning. When you say in computer technical terms, we need to do the feature extraction. We need to do the classification process. But in the deep learning, You'll be simply giving the raw data. Based on the raw data, it used to do the complete process. By seeing the image, it automatically do all the process. That is what we say it is the difference between the machine learning and the deep learning model. When you have to use the deep learning model, that is a convolutional neural network model. If your data is a two-dimensional data, what is two-dimensional? It is an image data, or if it is a video data, then you can go for this convolutional neural network model. This convolutional neural network model has the convolutional layers, it has the convolutional layers, and it has a fully connected neural network layer. What is this convolutional layer? This extracts the features. Extracts the future. It automatically extracts. You don't want to say anything, right? However, fully connected network, that is what we discussed earlier, feed-forward neural network, nothing but the classification problem, right? This is what we are going to discuss it now, okay? Right. So what we are going to discuss first is convolutional neural network, components, then hyperparameters, then hyperparameter optimization techniques. You can be a chemical engineer, you can be a mechanical engineer, you can be an electrical engineer, any kind of data. If it is a two-dimensional data or a one-dimensional data, you can deal with this convolutional neural network model. Okay, they say it as a deep convolutional neural network, or they say it as a convolutional neural network. What is convolution? Convolution is simply a mathematical operation, right? It is simply a Hadamard product of two data. Hadamard is nothing but dot product of, that is point to point product of any two elements is what we say it is a convolutional, or nothing but the Hadamard product, right? Here, I will show you that later on. So what we are going to do here, this convolutional neural network model is sparsely connected. It is not fully connected. Fully connected means it requires more number of weights. It requires more number of weight updations. The connectivity will be very complex and congested. So it takes a lot of time to update the weights. That is why they designed this as a sparsely connected multi-layer network with the parameter sharing. Parameter sharing means in one layer, some parameters will be used with the other layers. Especially, it's a special kind of an architecture that deals with one-dimensional and the two-dimensional data, right? It is not used for a zero dimension. Zero dimension means it's a textual data. It can be used with the three-dimensional. Three-dimensional matlab, it is a video, but the video has to be split into the frames, nothing but the images. Then only it can be processed. So what are all the components of the convolutional networks? Okay. So we have this as the convolutional layers. Then we have the pooling layers. We have the convolution layer. We have the pooling layer. We have the fully connected layers. Apart from that, there are something like a dropout layers are there. There are something like a dropout layers. Okay. First, let us discuss about the convolutional layer. Right? What is a convolutional layer? Convolutional layer is the very, very, very important segment or the layer for your future extraction process. Okay, it used to extract the futures. Nothing but convolutional operation over input data using a set of learnable filters. Here, there are some people, they used to have a doubt. For example, whenever you type any kind of a convolutional 2D model, what we used to do in the sense, CNN 2D, right? Then we have to give the number of filters. Then we have to give the filter size. And then we have to give the activation function. What is the number of filters? The number of filters are the learnable filters, learnable parameters. As like our weight and bias in the neural network model, these filters are the learnable things. During the back propagation, it will be updated. So how to fix the filter, the number of filters? For example, you are getting the input size of 128, 128, comma 3. That is, this is the color image, RGB. This is the width and this is the height. When I am doing this with the number of filters, that means let us take the number of filters as 64. What happens here after these two operations, after this convolution, we will be getting the size of 120. Okay. Before that, we have to fix the filter size as something like 3, 3. What is this 3, 3? I will explain. How it reduces, I will explain. Then how it converts. This original image is converted to something like 126, 126, 64. What is this 64? The 64 is nothing but the future maps. What is this future maps? Which is nothing but the futures that have been extracted from the original input image. I got my point. What is this 126? Why this 128 is become to 126? Okay. For example, you have an image of width 128 cross 128. If you do the convolution with something like 3 cross 3, we have the formula height of an image minus height of a filter plus 1. What is the height of your image? It is 128. Height of the filter is 3 plus 1. So 128 minus 3 will be 125 plus 1 will be 126. With the understanding that stride is equal to 1 and there is no padding. Okay. What is stride? What is padding? We will be discussing it later on. Okay. So many people, what they used to do in the sense, they used to take, even sometimes at my early stage of my career, I taken the code from other people, whatever they have written, that have been used by me, but it will not give you the best result. That is because of the number of layers and that is because of the number of filters they have used it. Right? That is the purpose. You have to understand the basic mathematical operations of convolutional operations. So convolution operation is nothing but it is slided over the learnable filters. The filters, number of filters and the size of the filters matters. So it is used to capture the specific patterns or the features such as the edges, textures, or the shapes. I will show you how it is. Then we have something like an activation function. What is mean by an activation function? As I said earlier, in convolution, we will be using mostly this ReLU. ReLU matlab, it is a rectified linear unit. What is the purpose of this ReLU? Whenever you get negative value, that will be truncated to the value of 0. If you get the positive value, that will be taken to the next process. Let us take a small image of size 3 cross 3. If this is an input image, let us take this as -1, this is 0, this is 3, this is 2, this is -3, this is 0, this is -3, this is -2, and this is 4. When I use a ReLU means f of x will be max, comma 0, right? Max is nothing but some kind of positive values. So it should be not max. It should be max of 0, comma x, which is nothing but even you take this, when you take -1 with the 0, -1 is the maximum value. So this becomes 0. Second one is also 0. Third one becomes 3, then 0, then 0, then 2. -3 becomes the value of 0, minus 2 becomes value of 0, 4 will be 4. This is the purpose of a ReLU. Why we make that negative values as 0? Why you cannot use that? We are not bothering about the negative values. If you take the negative values into the process, then it will leads to more number of 8 updates. That is why we are making that everything positive. Right? So next one is a filters. Small matrices, maybe 3 cross 3 or 5 cross 5. In many transfer learning mechanisms or the pre-trained mechanisms, they'll be using the size of 1 cross 1. 1 cross 1 will consume more time. So probably 3 cross 3 is the best size than the 5 cross 5, because larger the size will miss some patterns in the input data. Then the stride, number of pixels by which the filters moves out. That is what we said as the strides, right? Most of the time we used to fix the stride as 1. That means it will slide all the input positions. That is the purpose of the stride. Padding. Padding means it used to reduces the dimensions, right? If you use p is equal to 0, it will reduces the dimensions. If you use the padding as p is equal to 1, it will maintain the same dimension of the given input image. In your research perspective, you may think that whether you want all the data or not. I will show you an example. At the time you can understand. And then the activation function applied to introduce nonlinearity. As I said earlier, maybe the ReLU, or it can be any kind of data in this process. Right? Next, what is the convolutional operation? How it is going to process? Let me give a small example. We have the space mission. That space mission, actually, this is a mistake. I have not given the caption. Sorry for that. So we are going to track the space missions, right? The output is given with the time t. It starts with 0. It goes on with some timestamp t. So how we are going to calculate? This is a convolutional operation carried out in the one-dimensional, because the timestamp, what is the airspace? Airspace is given with the one-dimensional thing, right? So what we are going to do, how we are going to do that? See that this is the weight matrix, nothing but the filters, right? We have the position of the space machine. This is the position of a space machine. We have the position at different instances, times equal to 0, times equal to 1, times equal to 2, 3, and 4. So this is the weight matrix. So if you want to perform this W5, that is, if you want to identify this X5, then X5 is the convoluted operation of all these 5 instances. You see here, X0 with this W0, X1 with this W1, X2 with this W2, X3 with this W3, then X4 with this W4. This is what given here, 0.01 plus 1.00, which is nothing but X0 into W0. Then when you come to this, this will be X1 into W1. Like this, it goes on. Sum of all this value will be giving you this value of X5, which is nothing but 0.1401. As I said earlier, it is a point-wise multiplication. So we are not going to do the simple matrix multiplication. You see here, this is multiplied with this, this is multiplied with this, and this is multiplied with this, this is multiplied with this, and this is multiplied by this. This is what we say it as the Hadamard product. Okay. So let you take a two-dimensional data. This is an image, right? This is the filter. This is the filter. Okay. So when you slide it over here, right, we'll be getting the output of these positions, right? The next position will be moving like here, like this it will move. Then it will move here. Okay, like this it will move like this. So here stride is equal to 1 and the padding is 0. Okay, so what is the weight height of the image? It is 1, 2, 3, 4, 5. What is the width of the image? It is also 5. So what is the filter size? 3, 3. What is the original formula for this? In a sense, height of a convoluted output. This final output will be height of an image minus height of the filter plus 2p, 2p is nothing but the padding, plus 1 divided by stride. So height of an image is 5, height of the filter is 3, plus 2 into 0 will be 0, plus so 5 minus 3 plus 1 by 1 will be something like 3. So height of the convoluted image is 3. So you see here, this is coming as 3. Similarly, height of the width of the convoluted image will be width of the image minus width of the filter plus 2p plus 1 divided by s. Same thing, 5 minus 3 plus 0 plus 1 divided by 1, which is equal to 3. Right? So this is the figure shows the patches, okay, how it is done. So whenever we do this operation, after that, what we have to do in the sense, we have to do with this ReLU. ReLU is nothing but the activation function, where W0 is nothing but the bias. Okay. So we don't want to, this is the bias and this is a weight matrix and this is the original image. X is the original image, W transpose is the weight matrix, and based on this, we'll be putting all this input to the ReLU. ReLU is nothing but max of 0, x, right? This is the final output. Actually, it is not given into the ReLU, then it has to be given into the ReLU. This is an output without ReLU operations. So this is how the convolution operations. Let us take this. This is a 4 and this is also 4, which is multiplied with the 2 cross 2. So how the input of this first, which is given, right? 4 minus 2 plus 1 will be 3, right? So when I slide this with here, A with the W, B with the X, E with the Y, F with the Z, right? So that is the value of 1, 1. Similar way, when I slide it over here, right? Something like, when I slide it over here, what happens here? When I come over here, this will become W, this will become X, this will become Y, and this will become Z. Like this, the next operations will go on, right? So what is very, very important? Most of the time, you people will have the data in the 2-dimensional, right? So how to use the, first let us explain about the future maps. Future maps means whenever you slide the data, right? Whenever you slide the kernel or the filters, we'll be getting one output value. That is what we say it as the for future maps. The future maps is completely dependent on the data what we have. So n number of filters will create you n number of future maps. Whatever the number of channels that you have, if you are using number of filters as 32, then you will be getting that into that many numbers. As I said earlier, if my image size is 128, 128, 3, if I use with the 64 filters, then what happens? This will be converted to something like 128, 128, 64. These many times it will convert, right? In the one-dimensional data, one-dimensional means it may be any kind of a time series signals. It can be sensory signals. It can be ECG signals, anything. So one-dimensional filter is slided over the one-dimensional input. In case of two-dimensional, it will be slided over all the 3 channels. That is very, very important. It will be slided over all the 3 channels, and the sum of all these things will be given as a single output, right? So let us discuss with that. You see here, this is your R, this is your G, and this is your B, right? Let us take 3 channels. If you are using the kernels or the filters, let us have different filters, 1, 2, and 3. First, this will be slided over here. You will be getting some one value, and this filter is slided over here. This will be getting a value, and this is filter over here. This is getting a value, and the sum of all these things will be the final future map, right? You may ask a question that whether the filters will be different for different channels. Actually, for the first instant, it is no. But during the back propagation, these filters may change. That is why we are having the different channels and different kernels, right? But in the forward direction, that is a feed forward direction, we'll be using same filters for all the 3 channels, right? My question is, if you have the one-dimensional data, maybe that is, two-dimensional data with only one channel, something like this, 128, comma, 128, comma, 1. What happens? This will be converted to something like 128, comma, 128, comma, 64, right? That is a process of conversion for the one-dimensional. That is two-dimensional with a single channel. When we say it as a two-dimensional with a single channel, whenever you use the grayscale image or the black and white image, that time we have only the single channel. That single channel will be converted to the number of filters, right? So if it is a multiple channel, each and every value will be slided with the same filters or the different filters. Then all these values of that particular position will be summed up to get the final feature map. So we used to say this as a relation between the input and the output and the filters. So this is height. Height is nothing but height of an image. Depth is nothing but the number of channels. Then width is nothing but the width of the image. So this is the convoluted output. The depth is nothing but, this is D1 is nothing but the depth of the image. Depth of the image is nothing but the number of channels. Depth of the convoluted image will be the number of filters you have used. Height and the width will be based on the formula as I said earlier. Let me again show you that formulas. You see here, let us take this input image as 5. Width is 5, height is 5, depth is 1. Depth is 1 is nothing but the number of channels is 1. When I use the filter size of 3 cos 3, what will be the output? Since I am going to use the number of filters as only 1, number of filters only 1. So when I use the depth of 1, I'll be getting the output depth also as 1, right? It will not change. But what about the width? What about the width and what about the height? W2 is nothing but the convoluted output. Height H2 is nothing but the convoluted height. So W1 minus F plus 1. W1 is nothing but the width of the input image. H1 is the nothing but the height of the input image. So here W1 minus F plus 1, which is equal to so and so. Here they have not mentioned about the padding. They have not mentioned about the stride. So we directly calculate the output. This is called as a padding. What is meant by padding? Padding provides the convoluted image of same size. The padding can be either 0 or padding can be either 1. We cannot go more than 1. What is meant by padding? Padding in the sense, we'll be adding zeros at the leftmost column and the rightmost column and the topmost row and the columnmost row. So if you see here, for example, when you do the convolution operation of this, right? Over here, what happens? Some point of time, this will be useless. This may not be taken into the process of consideration. Again, this point and this point and this point and some point like here and some point like here will be missed out. That is why we are going for this padding. When I go for this padding, what happens? You see here, zeros are added at the topmost row. Zeros are added at the down row, that is the last row. Then zeros are added to the rightmost column and zeros are added to the leftmost column, right? When I stride over with the kernel, you see the size 1, 2, 3, 4, 5, 6, 7. This is the size of 7 cross 7. This is the size of 3 cross 3, right? What is the padding? Padding is given. This is the formula W1 minus F plus 2P. So W1 minus F plus 2P in the sense, width is nothing but 5. 5 minus 3. 5 minus 3 plus 2 plus 1, which is giving you the value of 5. Why it is 2P? You may ask a question that you have used the padding value as 1. But why you are using the padding? Why the formula is given with the 2P? You see the width. Which one is the width? This is the width. When you take the width here, we have added this as one row. Let me use a different color. When you take this, we have added one column here and we have added another column here. So we have taken 2 columns. That is why it is 2P. Similar way, when you take this height, what is in height? This is your height. Again, you see, you have added one row here. Again, you have added another row here. That is why it is 2P. Got it? last we have the stride. How we are going to move? So if you increase the stride, then the output what you are getting will be very less. I will show you. Actually, since it is a latex, we will not get. So let us take this as an input example. This is a 4x4 matrix. Let us have a 3x3 matrix. If I slide over here, when stride is equal to 1, what happens here? When S is equal to 1, first it will be slided over here. Then it will be slided over here. That's it. You cannot slide it more. Again, it will be slided over here. Then it will be slided over here. So 4x4 with the 3x3 will be 4 minus 3 plus 1, which will be around 4 minus 3 will be 1. 1 plus 1 is 2x2, right? If the same image, if the stride is equal to 2, that means we'll be missing one column. So first time we'll be sliding here. There is nothing like that because we cannot slide it here. If I slide it here, you'll be missing some values. You cannot process it here. So again, this is the only one you can get it. That is 4 minus 3 plus 1 divided by 2, right? Which is equal to 1, right? This is how the stride will be fixed. Whenever you use a stride, your dimension will be reduced, right? That is the purpose of stride. Okay. So we most of the time we will not be skipping the pixels. That is, we will not be using the stride. If you use a stride, then it will lead to some kind of distortions in your output. So you see here, this is a future maps. I got it for some convolutional layer. Okay, you see this is the original input of a cat. Okay, this is one future map. This is another future map. This is another future map. This is another one like this. You see the difference. Some eyes are there. Sometimes the body is there. Sometimes the cat itself is there. Sometimes the ear will be very clear like this. They used to identify the future maps. So next one is the pooling layer. What is the purpose of the pooling layer? If you want to use the pooling layer, pooling in the sense it used to reduce the dimensions, right? It used to reduce the size of the convoluted future map, right? It can be max pooling, it can be average pooling, right? There are n number of pooling layers available. What is max pooling? So this is the image of size 4x4, right? This is the image of size 4x4. But we got the output as 2x2, right? So we have used the stride value as 2. Okay. So that is why it is looking like this. So when I put this max pooling layer here, first it will be slided over here. So out of these four, which one is the maximum that will be taken as an output here? So 12, 28, 12, we'll be getting that output as 20. 30, 0, 2, 0, which will be taken as 30 because the maximum value out of these four that is fixed out. So when to use max pooling layer? Most of the time, 100% in your research perspective, you have to use only the max pooling because we are looking for the highly interesting area. We are not looking for the colloquial or the average area. That is why we used to have the pooling layer as to reduce the dimension of the convoluted future map. So this is the max pooling layer. You see the image of this. This is up to 1000. But you see this size, this is up to 500. Similar way, you see the convoluted image of that is a max pooling layer output, it is 250. The here is 500. That means whatever the dimension that we have, that dimension is converted to half. How it is converted to half? Whenever you fix the stride as 2, automatically the pooling layer will use the stride as 2. That is why the dimension is reduced to half, right? So, right, this is about the pooling layer. Now we have the fully connected neural network layer. Before going to this, how to fix the, okay, let me first explain this, then I will give you about the number of layers, how to use the number of layers, how the chemical engineering person has to use the number of convolutional layers, or how the mechanical engineering person has to use the convolutional neural network. Let me explain it. So this is what I mentioned it before, that is in the previous session. It is a fully connected neural network model. This fully connected neural network model is nothing but the layers which is connected to finalize the classification output, right? It is just to identify what is the targeted class label. That is the purpose of the fully connected neural network. You see here, this convolutional layers have less number of connections, nothing but the sparse connections. However, the fully connected neural network has the dense connections. Each and every node is connected with all the nodes of output. You see, one is connected with all the nodes of A, B, C, D. Similar way, 2 is connected with all the nodes of A, B, C, D. 3 is connected to all the nodes of A, B, C, D, like that, right? But when you take the convolutional layers, it is not mandated that each and every node has to be connected to each and every node of the next layer, right? So, right, before entering into this, I will show whether the screen is visible to you,
Yes, sir.
whether this text editor is visible to you.
Sorry, sir, you have edited anything in the PPT?
No. Whether the text editor, what I am showing, is visible to you.
No, sir, it's not. Only the
Okay.
presentation is
Okay.
visible.
Now you are getting this text document.
Yes, sir.
Well, let us take an example of 128, 3. This is an input image you are giving to the convolutional layer number 1, right? Which is having the filters of size 64 and the filter size is 3, 3, right? Then activation is something like the what happens here, this will be converted to something like, as I said, if you are mentioning only this, which is understanding that stride is equal to 1 and padding is equal to 0. Okay. So automatically 126, 126, 64 will be the output. Now, what is the input to the second layer? 126, 126, 64. Have this as the convolution layer number 2. Again, the number of 64, the size is 3, 3. Activation is ReLU. What happens here? The input size 126, the same formula whatever we mentioned. So that will be 124, 124, 64. Now I am going to use 124, 124, 64 with the max pooling layer, right? So in the max pooling layer, you cannot mention the number of filters. You cannot mention, but the number of filters is always 2, 2, right? It is understand that stride is equal to 2 and padding is equal to 0. And there is no activation function here, right? Then what happens here as per the formula, 124 is divided by 2, nothing but 62, 62, but the number of channels will never reduce. That will be maintained as 64. You got my point? I have an original input image of size 128, 128, 3 that is given to the first convolutional layer, which reduces the size to 126, 126, the number of other filters you use. When I give that as an input to the convolutional layer number 2, which converts that that is 124 comma 124 comma 64. When I use this 124 comma 124 comma 6 with the max pooling layer, it will reduce the dimension to half, that is 62 comma 62 comma 64. If I am using that with a convolutional layer 62 comma 62 comma 128, then the convolutional layer number 3, let us take the number of filters as 128 and the number of filter size is 3 comma 3 and activation as value, then this will convert that value to 60 comma 60 comma, instead of 64 it will be converted to something like, right? Finally, when I take this 60 comma 60 comma 128 with a max pooling layer of 2 with a filter size of 2 comma 2 with the stride is equal to 2 and 0, then what happens? It will be converted to 30 comma 30 comma 128. Now, what you have to do in the sense, as we discussed earlier, the fully connected neural network will the vector. It can be the row vector or the column vector. It cannot take the two-dimensional data. However, here we have the two-dimensional with 128 channels. So how it will be? We have to use the layer called as a flattened layer. Flattened layer matlab, it will convert this two-dimensional with the number of channels into the single point. That means 128 into, sorry, it is something like 30 into 30 into 128. So it is something like 1,11,5200, which will be given as an input to the fully connected neural network. Got my point? Now the fully connected neural network, you can fix the number of units, maybe like 512 or 1028, or it can be more than that also. The number of units in the hidden layers, like that it will do for the process. Now, okay, let me come back to, I think now the PPT is visible, right?
No, sir. Still the document.
Text editor is there, right?
Yes, sir.
Okay, now let us discuss how to fix the number of layers and all these things, right? This is what we say it as hyperparameters. The hyperparameters are two parameters. One is the learnable parameters. That is, second one is the what we say it as the network parameters, right? But it will not learn through backpropagation. It will be identified only by means of the process, right? So we have the architectural networks, architectural parameters, and the training parameters. Let me explain one by one. First, very importantly, how to fix the layers. It is going to determine the depth of the network, right? So you may be any kind of an engineer. If you want to use a convolutional neural network model, use the less number of depth. That is, use less number of filters, maybe 64 or 32 or 16 in the initial levels, and simultaneously increase the number of filters to the maybe like you can fix 16, then you can fix 32, then you can fix 64, you can fix 128. Don't go beyond this 128. Okay. How to fix the number of layers? If you are very well in mathematics, as I said before, you derive how to reduce the number of inputs that is given to the fully connected neural network. If you reduce that, the number of units, that is, you don't bother about the number of channels, bother only about the dimension of the image. If your image is reduced in a good manner, then the fully connected neural network will do the process at the best. So don't give the input something like maybe something like 256 comma 256 comma 64 as the input to the flattened layer. Don't give it like this. This is wrong. You better reduce. That is fixing the number of layers. If you increase the number of layers, then the depth and the size of the image will get reduced. So what is the suggestion is, if you are using 2 convolution layer, use a max pooling layer. Whenever you use a max pooling layer, it will not make you overfit. 2 convolution layer, 1 max pooling layer, 1 or 2 convolution layer, max pooling layer, then you can go for a flattened layer, then you can give it to the process. Don't give more number of convolution layers continuously, that will make you to overfit, right? Then how about the number of filters? In the first level, use less number of filters, then use more number of filters, right? That will not make you more computational cost. If you use more number of filters at the first, it will make the computational cost very higher. So maybe the initial level of layers may have less number of filters. Later on, you can increase the number of filters, right? Size. Smaller the size of the filter will capture you finer details. Larger the size will miss you some kind of informations. So better to use the size of 3x3. Then stride. 100% use stride is equal to 1. Don't skip any pixels, right? So you see that larger the stride will reduce the spatial dimensions, but you may miss the important informations, right? Padding. Most of the time you will be using valid, no padding, right? Because we never bothers about the corner. But if your data is highly authentic, you want to use that corner data, you can go for padding. That is same. It will convert the size of the input image to the whatever the size that you require. Then finally, the activation function. Most of the time we'll be using relu. Sometimes we'll be using leaky relu. Leaky relu is nothing but we'll be using something like max of 0.01x, x, right? This will allow you to include some non-negative values also, but the non-negative values will be very less, right? That is the purpose of this leaky relu. Then the pooling size, most of the time we use only the 2x2, reduce the dimensions with the stride is equal to 1 to 1. Then finally the pooling layer, it can be max or the average pooling. 100% you'll be using the max pooling layer. So if you want to design the convolutional neural network for your own data, don't take the data from anyone else model. Use your own model, right? Start with a single convolutional layer, connect with the flattened layer, connect with the fully connected neural network model, check the output. Second time, if the performance is not satisfactory, you add one more convolutional layer, put with the pooling layer, then flatten layer, then check with the fully connected neural network. If it is not satisfactory, 2 convolution layer, pooling layer, convolution layer, flatten layer, then fully connected neural network. Like that, you increase the layers like 1 by 1. Accordingly, you have to check the filters and the filter size. Very important parameters. This is a training parameters. We say it as an optimizers, learning rate, batch size, epoch, all these things. So what is an optimizers? How we are going to update the weights? That is what we say it as the optimizers. We say it as a back propagation mechanism. The back propagation mechanism, the gradient descent, batch gradient descent, everything is what we said is an optimization algorithm. That is why they mentioned that as an optimizers. Learning rate, how fastly you will attain or your data adapts to the network. That is called as a learning rate. Let us discuss one by one. So optimizers, you see this method used to update the weights to minimize the loss. That is called as an optimizers. It can be stochastic gradient descent, batch gradient descent, RMS prop, ADAM, ADAM W, ADA delta, ADA grad, ADA max, NADAM, all these things are there. Okay. So very popular algorithm is the stochastic gradient descent, as what I discussed in the previous session, right? So it used to update the weight for each and every instance of the data. That is why we say this is a stochastic gradient descent. It is highly time consuming, but will perform better. You see here, it's a variant of a gradient descent algorithm. It used to update in the sequential order. It predicts the future data at each and every step. You see here, first we'll be taking this first instance, we put it to the network, we'll identify the error, we'll update the parameters. Then second instance, again the network. So like this, each and every instances will be taken. For each and every instances, the data will be checked based on the error rate and the weights are updated. Highly time consuming, computationally expensive model. This is the stochastic gradient descent. Second one is the batch gradient descent. Batch gradient descent is nothing but entire data as a single batch, which will be given to the process of neural network or convolutional neural network. Based on that, error will be updated. Error is calculated. Based on the error, the weights will be updated. And then the second time, the process will be carried out. So this is the difference of the batch size. If you use the batch size as 32, 64, 128, 256, accordingly, the weights will be updated. To be frank, many people used to fix the batch size as something like 128 or 64. They actually don't know why the batch size is fixed, right? The batch size will make you to update the weights. Based on the batch size, the weights are updated. Lower the batch size, weight updation will be the best. It may be time consuming, but it will perform better. For example, if your data set size is something like 1000, you can better make the batch sizes 60 or 64 or something like 96 or 128. Don't go beyond 100. Okay. It can be the multiples of your learning rate, your batch size. Then we have the percent. Here we'll be discussing, it is actually, it will be updated based on the multiple batches what you have mentioned. You see here, the green color, first time 321 is updated, then 478 is updated. Then for the second batch, 567157 is updated. At last, 635246 is updated. Like this, every time the process will be updated for each and every time. This is the process what we say it as the mini batch gradient descent. Mini batch gradient descent is nothing but it is used to update the weights based on the mini batch value what you have been giving. There are the difference between the mini batch and the batch. Batch means the complete set of data will be given for the process. Mini batch means a part of the data will be given. But this mini batch is different from the gradient, that is a stochastic gradient descent. So this is the difference, how the cost is reduced, how the gradient descent curve, we say it is a bell curve, how the minimum value is attained, right? When you use the batch gradient descent, the curve is something very smooth. If it is a stochastic gradient, there will be a lot of ups and downs. Mini gradient descent, there will be something wobulations. Most of the time, we'll be using the mini batch gradient descent. That is the current process which is used in the all convolutional neural network model. Then the learning rate. How quickly the neural network updates its parameters. That is what we say it is a learning rate, right? You see here, the big learning rate means you may miss the minimum value. It comes from here, it jumps somewhere. So smaller learning rate means it will come down properly to the minimum. So you better take minus 10 to the power of e power minus 4 to 1.0, not starts with the 0. That is mostly minus 0.1 or 0.00, not minus, it is hyphen. 0.1 or 0.01. There is no learning rate with the negative value. Learning rate will be actually positive. Decay learning rate means the data used to reduce it. Actually, it stepped down by line. That is the purpose of the decay learning rate. Then the epoch. Epoch is nothing but the number of times the entire training data set to the network. That is called as an epoch. More epoch will lead to better training. For example, we used to say that whenever you used to drive the bicycle, we used to drive for the multiple times. It is not a matter that for the first time itself, you have driven the bicycle very clearly. You might have used the drive cycle for multiple times. That is why you are driving the bicycle now very, very clearly. So the more the number of epochs, your model is well trained, right? Finally, we have the weight initialization method. Actually, the convolutional neural network model will automatically initialize the data using the Xavier initialization method. So you don't want to mention anything about that. So if you are a fresher with this convolutional neural network model, you can automatically use the Xavier or the random initialization method. So you don't want to specifically maintain or specifically mention the weights. Then the regularizations. Regularization is mainly used to avoid the overfitting problem, right? That is L1 or L2 regularization can be used. L1 is nothing but the lasso regularization. L2 is nothing but the ridge regularization. My kind suggestion is, if you are a fresher in convolutional neural network model, don't go for this L1 or L2. Sometimes it may miss you or it may give you some distortions in your output, right? So better to use the other parameters, right? So with this, I will stop here because it may go for another 20-25 minutes. So before that, I want to discuss with you all, because if you have any doubts, you can clarify with me. Because this hyperparameter optimization technique, there are n number of techniques available that is used to fix the hyperparameters, nothing else, right? There is something called the grid search method, random grid search method, half random is there, half grid is there, lot of methods are there, even something like a genetic algorithm, even evolutionary algorithms are there, right? You can mix. Mostly the mechanical engineering people, what they used to do in the sense, they are very well versed in the optimization technique. So they used to club this optimization technique with the convolutional neural network model to get some good results, right? So, but in my point of view, what I am suggesting is, if you are a fresher with this convolutional neural network model, what you can do in the sense, you can start with the initial layer, that is a single, and you can go further, right? So now let us go for this question and answer session. Whatever the questions that you have, you can ask me.
Sir, they've been posting questions throughout the session. I'll
1 minute.
read it.
1 minute. Yes, you can ask any kind of questions. Someone is asking, please repeat the fourth. What is that fourth one? I'm not sure with the fourth one.
Sir, they are asking what is the relation between computation cost and epoch?
Computational cost and the epoch. Actually, computational cost in the sense, how much time takes to complete the execution. That is what we said is a computational cost. Actually, computational cost means we used to say it with algorithmic notations, right? But here, computational cost in the sense, how much of time it takes to train the model. That is what we say it as a computational cost here. If you increase the number of epoch, for example, your data set size is very huge. In that huge size, if you increase the number of epochs, it may take more time to complete the training process. Then obviously, your computational process will be very heavy, right? Then how are batch size and epoch are related? Very good point. For example, you think I have 100 data instances and my batch sizes, I am using the stochastic gradient descent. In that time, what happens for each and every epoch, I'll be giving all the instances, that is 100 times, I'll be giving the instances for training. For each and every 100 instances, then it will be multiplied. For example, let me share so that you can understand. See, I have the total number of instances. Total instances is equal to 100. So let us take the batch sizes, something like 5. So how many times it will update? For each epoch, 20 times the weight will be. So if it is 100 epoch, 20 into 100 times, which will be 2000 times the weight will be updated. Yes, it is depends upon the batch size. If the number of batch size is less and the number of epoch is high, then the number of times it updates will be more. It is very close to the stochastic gradient descent. Anyone else? Any other questions? How does the random search for hyperparameter tuning? That's what I said. Na? So random search means we'll be used to have the random process. Okay. That is kind of an exhaustive search selection. Based on that, we used to identify the futures. Grid search in the sense, we used to change the grid value. Based on the grid value, we'll be getting an output. Bayesian search is completely based on the principle of Bayesian optimization. That is the Bayesian conditional probabilistic approach. Using that, we used to update it. Very importantly, which method you want to use. Better thing is if you are a beginner and your model is not that much robust, that is not that much hybrid, then you can go for the simple grid search CV method, right? So that would be the best case to identify your solutions.
Sir, they have asked if we want to work on ultrasound images, then will can CNN be used?
Yes, probably, but I'm not sure with the ultrasound images. Maybe if your ultrasound images is two-dimensional with the multiple channels, definitely you can use this convolutional neural network model. First and foremost thing, understand how you can extract the features for each and every convolutional layer and how the convolutional layers can be spatially reduced by means of the pooling layer. Based on that, if you use, then it will be used to identify the class. Definitely you can use. What is the rule to select the number of layer and the filter in CNN? There is no rule directly. How you can fix in the sense, if you use more number of layers without the pooling, it will lead to overfitting. If you use more number of layers with the high number of filters, that will also makes to overfitting, right? So first and foremost thing, if you understand the mathematical background, you just derive it as like I have given to you. Derive it, you converge the given image to some dimension. That is like, for example, if your data set image size is 128, 128, if you reduce that into something like 24, 24, right? It would perform better. It would perform better. It will actually have the good features what you are expecting, right? If you have 128, 128, but you are giving that to the input of fully connected neural network as something like 120, 120, then you will not get enough number of features, right? It will simply increase your number of feature maps. Increase of feature maps will increase the complexity of your fully connected neural network model. That is what I am saying you. Decrease the size of the image, but you can increase the number of feature maps so that your fully connected neural network will perform better.
Yeah, they have asked how to select number of layer and number of filters.
That is what I am saying. Na? If you are using the number of layers and the number of filters, I have explained to you in the before session, that is the same session only. I have used the text editor. If the input image is so and so, if you are applying the filter and if you are applying the number of filters and the filter size, how the size of the dimension, new dimension is coming. For example, we have mentioned earlier, if it is 128, 128, 3. If I use 64 filters, then what happens? Convolution layer 1. If I use 64 filters, then I'll be getting 128, 128, 64. You see here, the three channels is converted directly to 64 channels, right? In this case, what happens? There may be chances of the important features available at different channels, right? Three channels available at different 64 channels. So what is the best option? If I use 128, 128, 3, if I use this convolution layer 1 with the 16 layers, 128, 128, 16. That means whatever I am expecting, that is available with 16 number of feature maps. Now what you can do, you can now change. Sorry for this. This is something around 126. 126. 16. If I give it the convolution layer number 2, if I change this into 32, what happens now? 124, 124, it will be something like 32. So step by step, you have to increase the filter size, and step by step, you have to increase the number of filters. Don't simply use the higher number of filters so that you may get the enough information. Okay. If you use less number of filters, whatever you are expecting, that will be scattered in the less number of filters. There is a less number of feature maps so that your classification can be done perfectly. For example, in the first instant itself, you are changing the 3 channels to 128 channels or 3 channels to 256 filters. Then you may not get the proper value what you are expecting. Right? Sir, can any algorithmic improvements in standard CNN be done so as to improve the classification performance? And if CNN works like a black box, then how can future maps be expected? Very good point. What you can do in the sense, you can combine this convolutional neural network with something like an explainable AI concept. What is the purpose of explainable AI? This will explain you whether this data is important or this data is important or this data is important, or why this output comes because of this particular explainability. That is why we say that as a explainable AI. So if you use the explainable AI, something like CRAD-CAM, there are n number of techniques available. If you use that, you may get the proper results. Yes, you can under your question is exactly correct, right? You do one thing, you take a less amount of data. For example, in your medical image classification, if you have 1,000 images and your classes is 3, right? Or your classes is 2, okay? 1,000 images of class 2, 500 images, 500 images. If you run with this 1,000 images, it is difficult for you to analyze this problem. So what I'm suggesting is you take a less amount of data, a random data, maybe 10 images from class 1, another 10 images from class 2. Run with the sample model. As I mentioned before, single layer, 2-layer, max pooling layer, third layer, max pooling layer, flattened layer, convoluted, fully connected neural network, like that you run out. So 10 plus 10 images will be 20 images. If you run it with this 20 images, if it performs better, then when you use it with all the 1,000 images, the performance will slightly degrade. It will not degrade that much, right? So like this, you have to use with the less data, with a good layer, with a good model, then you'll be getting some optimal performance. Sir, is there some specific conditions where particular optimization should be? See, I have not clearly explained about all the optimizers. In the convolutional neural network model, Adam or Adam W is the best optimizers, right? Because the stochastic gradient descent, batch gradient descent, and then the mini batch gradient descent is highly costly and time consuming. So we'll be using that only for the neural network model. If you go for the convolutional neural network model, we'll be using only with Adam or Adam W or Adam grad, right? It is somewhat based on the distribution of the data, what we have, okay? So kindly refer to some books, so you'll be getting more informations. You are asking about the number of epochs for a given problem. So number of epochs is nothing but you can fix with the 10, minimum 10. It depends upon the data set size, what you have. You start with the 10, you increase that to 15, or you increase that to 20, or else multiples of 10, 10, 20, 30, 40, 50. At some point, if your accuracy is saturating, then you can stop the epoch. You don't want to increase it further, right? For example, for 10 epoch, you are getting the accuracy of 92. For 30 epoch, it increases to 94. For 50, it is increasing to 97. And for 60, it is again 97. For 80, it is 97. Then you can stop at 50 itself, no problem. How to decide the number of all the layers looking at number of data? Yes, madam. Actually, again, I am saying this is completely based on the mathematical understanding, right? So I'll be sharing some content with the coordinators. There will be some mathematical calculations. With that, you can check it out. Is it number of layers in CNN models are depend on the image size? Yes, exactly. The number of layers depends on the image size. How we are going to extract the features from the input image. That is based on the data what we have. Really, I'm sorry. I don't know anything about this biomarkers in MRI and fMRI scans. I am sorry. Actually, I worked only with this one-dimensional data with some computer, with some, what we say is a different kind of process. Any other doubts? Mathematical model behind convolutional operators design. See, if you want to know this mathematical model behind this convolutional operators, what you can do in the sense, first you have to know about the, what we say it as the backpropagation process. That is a forward pass and the backward pass. And based on that, you have to identify the number of filters. Okay. So definitely it requires another session to explain that mathematical operations. You can refer with MIT courseware. There are some number of what do you say it is availables. Some kind of things are available. In NPTEL, there is a algorithm, there is a subject called as, let me give you that, machine learning for engineers. This is an NPTEL course. Dr. Professor Balaji Ramakrishnan from IIT Madras. I think I forgot the another name. The another one is going to take the class maybe tomorrow or day after tomorrow or yesterday, I think. Ganapati Subramaniam. Professor Ganapati Subramaniam. These both are the fellows. They have taken this course. You can refer to this course. No. You cannot use the CNN for the future selection purpose, right? CNN can be used only for a future extraction purpose. Yes. Ablation study is highly important when you go for implementing this model and you go for the research papers. Your ablation study is highly mandatory. Without ablation study, they will not accept the paper. How do we mix the convolutional layer with ReLU layers? ReLU layer is nothing but the additional layer which is used to identify only the positive values. That's it. That is the purpose of the ReLU layers, right? So if you use, already you have used the ReLU activation function in each and every convolutional layer. Apart from that, if you use a ReLU layer, then it is a dual purpose only. It will be extracting only the positive value, right? If you use a ReLU layer again also, then you will be taking only the positive value. That is of no use. You are saying that RL means reinforcement learning, right? Reinforcement learning is based on the environment, task, and learning process. Yes, you can update it. It is currently under the research avenue. You can do it. Involution neural network, I am not very clear about this involution neural network. I have not explored that much because it is under our research study currently. I don't have any channel. Yes, you can combine both CNN and INN. Hope so, but still now we are not checked. So this is my mail ID and this is my contact number. In case of any kind of collaborations, you can contact me, or in kind of any doubts, you can call me. No issues. I thank especially this Dr. Chandra Kumar, Dr. Parthasadi sir, and Sasi Rekha madam for this wonderful session. Okay, I think I shared my knowledge to you all.
Yes, it was
Madam,
very
actually,
useful.
one minute. Sorry for the interruption.
No problem, sir.
Gomadi madam is asking that explainable AI. Actually, madam, explainable AI is nothing but which will discover the black box, right? Whatever the black box model that we have, why this black box model is giving these results that can be interpreted by the explainable AI models. When you use the normal machine learning, you can use something like a Lime or SHAP model. When you go for the convolutional neural network model or any kind of deep learning model, there are n number of explainable models like a GradCam, SwitchCam, like that is available. When you combine this with the CNN model, you will be come to understand which features are important, which features are not important, which feature map will give you the better results, right? That is the purpose of an explainable AI. Okay. So for example, you are applying a loan in the bank. They simply reject without saying the any reason. How come you will accept that? Right? So if you want to dig deep into that, we can connect the ML or DL with the explainable AI. That's it. Thank you. Yes, please. Varsha Mitra, you can.
Yes, sir. So thank you. Thanks a lot for joining us today and sharing your expertise. And also thank you so much for patiently explaining every concept, sir. Like even we both were listening and taking notes on that. And sir, thank you so much for answering the questions patiently also.
Thank you. Thank you.
Yes, sir. So that brings us to the end of, yes, sir.
I have given the mail ID and my contact number. If you want to mail anything for this purpose, you can mail or you can text me in the WhatsApp.
Yeah, sir, sure. We have also
Thank you. Thank
noted
you.
it.
Thank you.
We will send all the participants also.
Sure.
Yeah, sir. Thank you, sir.
Thank you,
So
sir.
that brings us to the end of the day 2 of our FTP. Today's sessions provided a deep dive into the deep learning techniques, object recognition, and AI-driven clinical analysis, enhancing our understanding of AI's impact on healthcare. We appreciate the engaging discussions and active participations throughout the day. And also for the participants, we all have just a reminder. The assessments will be conducted at the end of the program. Minimum 80% of attendance and 70% mark in the test are required to obtain the certificate. As well, we will also be sharing the proof session recording in the YouTube for monitoring. Like the recorded session will be uploaded in the YouTube. So we ask you to maintain the attendance at least at the minimum of 80%. Kindly provide your valuable feedback by we will just share the screen. You can just scan the QR code or we will give the link in the chat box.
Okay. Thank you all. I am leaving now. Huh?
Yes, sir. Thank you.
Thank you.
Thank you, sir.
Yeah, we have sharing the QR code. The link will also be sent in the chat box. Thank you, participants. You can leave if you have just filled up the feedback form. And also please remember that tomorrow's session also starts at 6 p.m. sharp.
Parsha, ask Anu to end the session.
Okay, sir.
Since she is the host, she can only end the meeting.
Okay, sir. I'll ask her.